Welcome to the online streaming primer from IET Media. IET Media is the Institute of Engineering and Technology's technical network for engineers involved in all forms of media. Our presenter today is Russell Trafford-Jones. Russell's a broadcast engineer with wide-reaching experience within the industry, running and designing broadcast infrastructure at all points in the chain. As part of the management team at Video over IP specialists TechX, he develops new services and builds class-leading customer support. Russell's passion for education shows in his work as an executive member of the IET Media Technical Network and as the editor of thebroadcastknowledge.com, an RTS-nominated site which features a new educational video every day to help engineers throughout the industry keep on top of new technologies and ways of working. Over to you, Russell.
Thank you. Today we're going to talk about online streaming because it is everywhere, and I think there's a lot to be gained from understanding how it works. So we want to look at how we got where we are today, and also we'll finish off by just looking at a little bit about what the future might be. So we're going to do that by looking at what broadcast is in general. Let's go and see what we're trying to do, what we've always been trying to do, and what are the benefits, what are the downsides of how TV was originally created and evolved. Where did this demand for being online come from? And what does it really mean? What's the essence of what we're doing? And then we'll get on to how it works. We're talking about words like chunked encoding, streaming formats, and then with a look at standardization in the future, we'll have a good understanding of the basics of what people are doing when they say they're doing online streaming. So looking at broadcasting for a moment, we've been doing broadcasting for many years, whether it's be TV or before that radio. Fundamentally, all we're trying to do there is get a single signal to many receivers. That's the definition, really. We can do that with cables. Might have to be a cable to each TV, but each TV is receiving the same thing. Terrestrial TV like Freeview, then we're going to be using a single transmitter, and then that will transmit to a local area, and everybody will get that same number of channels. Satellite's the same, but it could actually, from so far up above, it can hit a whole continent at a time. So, that's really efficient in terms of a transmitter. You can put that up in radio, for instance, and hit a really wide area with very little effort. And that, in a sense, has been very powerful, hasn't it? In all of this time, using broadcast over the airwaves, it's been democratic in the sense that anybody can get a radio, anyone can get a TV. We're all receiving the same thing. There's a great power, of course, for governments, but there's also, it's a great leveler as well. It's good for both sides if we can get that balance right. So broadcast, in the way we've been doing it for a long time, has been practical at very large scales. It's not always been easy to do broadcast, and everything we're going to talk about relies on the fact that we can actually record what we're doing and use it again later. And I think it's kind of humbling to realize that when we started, 1936, at the BBC, we were pushing the boundaries of technology at that point, so much so that nothing could be recorded. If you had a film camera, sure, you could record what was going on. But when things were going out on air, that wasn't even possible to be recorded for many years. And there were other benefits, though, at that time for the fact that broadcast was tricky to put off, but fundamentally it was simple enough that there was almost no delay, and that was true for many years. As long as analog continued, you almost instantly seeing the action, you're almost instantly hearing it. And so much so that you could, when television couldn't carry stereo, you can see here from, there's a paper clipping here, Star Wars, if you want to listen to this in stereo, listen to radio FM. You get the FM stereo experience on your mono TV. And that was done in many countries. Nowadays, that's not possible. It's not practical, at least, because we've moved over to digital transmission. That's brought us some benefits. In general, it's regarded as better reception, but it requires time to encode, time to decode. Different devices will do it in different ways. You're looking at different times. It's not going to be enjoyable to listen to one device and watch the other. So we started off with something very powerful, analog broadcast. There's no delay, but there were some downsides. And one is that if you look at how much of the radio spectrum it was using compared to digital, it's quite a lot. So we've been moving to digital transmission across the world, although in different ways, and that has brought us benefits. It's brought better reproduction of the video. Analog always suffered the further you got away from the transmitter. There was some form of degradation. It was a slight blurring, slight snowiness, perhaps. Digital broadcast, you almost always get exactly what was broadcast, and we've ended up with more channels. If we look in most places that have got digital terrestrial, there are more channels available to more people over the air. So that's where we've come. We've accepted some delay. We've got some benefits. And to be honest, watching something 3 or 4 seconds later isn't so much of an issue. Are there more things we can do? Well, let's take a bit of a look at the downsides that perhaps we could fix in terms of what does traditional broadcast provide us? Well, reception indoors can be a problem. We know it's made really to stick an aerial on your roof. Absolutely, it can be possible indoors. You can find that perfect spot in your living room and your bedroom. But if you were to then move around, it's not, you wouldn't expect to necessarily get a good signal and everywhere. The aerial is relatively big compared to today's aerials and mobile phones. You don't even see aerials in mobile phones. There are actually several inside, all carefully picking up the signals that it needs to pick up. But also, if you think about how we're going to use these things, we've got people spending time with their phones. My screen time says that I use it for work, I use it for sat nav, I use it for all sorts of things. When I come home, I watch stuff. It says that I'm using the phone 8 hours a day. So I'm spending all that time with that phone. Is it not sensible to expect it to do a bit of TV, to watch something that I want to watch? But I don't want to have a massive aerial sticking out of it. On top of all of that, if I'm on a train, I want to be able to watch it. And these transmission technologies deliberately weren't designed, because there's always trade-offs to be made. For people moving at speed, your reception is going to be worse. And of course, always been a problem. Do you get to choose what program you watch? Not really. If you're half an hour late back from work, you're half an hour late in terms of watching the TV. What you want may have finished or maybe halfway through. So there's always been that frustration. So now we can look at streaming. It's an ability to get things from, whether it's a video or radio, over the internet. Typically, you can stream in many different ways, but most people, when they say streaming, what do they mean? They mean using the internet. So we're using the internet to get a video from one place to another. You can do this on any network, but it's actually the unreliable ones, like the internet, which streaming in its modern sense has been designed for. It's been designed to be a bit more robust. But it's just as relevant and useful in corporate intranets. And ISP networks, if you've got an ISP, a nationwide ISP, for instance, they've got a bit more control over their own network, a little bit more, not a lot. In terms of by the time it gets to someone's house, it's still going to be potentially it's still going to have problems. But the more control you have, the less worry you have over how you stream and how many problems your data is going to suffer before it finally gets to its destination. So streaming is a broad term, and we're going to use it in a couple of different ways. Hopefully we'll be careful about how we explain streaming in the traditional sense and streaming in the online sense. So I think this is to start looking at really why we're even doing this, what's driving it. And I think there's a big aspect from the evolution of audio. Audio's always achieved things sooner in terms of adopting technology than video, in the sense that nowadays things are digital. You can achieve things quicker with audio because it has a lower bit rate. So it's less computation, network demands are a little bit less. It makes up with it in complexity and scale, absolutely. But nonetheless, back in the 1990s, it then became popular and actually practical for the first time to store lots of different songs onto a portable player. And of course, the iPod famously was released in 2001, and the promise was the marketing slogan, 1,000 songs in your pocket. And absolutely, that's smaller than some people's music library, but that's a lot of songs. It starts giving that feeling of a really useful, significant choice. What do I want to listen to? What mood am I in? So that has always been a very motivating factor in terms of what people want. So that has driven the industry in terms of music, and we're now ending up with things like Spotify, where we can choose from an infinite variety. Streamed audio at a similar time started appearing on the internet, and things like Shoutcast and Icecast are technologies and services essentially which allow you to create your own radio channel, a radio station. So all of a sudden there's a proliferation of specific niches of different music and speech which weren't really possible or practical before. So now we've got this kind of ability to choose what song to listen to when. We've got a lot more choice. It's only natural to say, well, yeah, I can hear it. Why can't I see it now? So in terms of streaming, what we mean really is it's video that arrives while you're actually watching it. It doesn't arrive earlier. Downloading things from iTunes happened a long time before. You can do that, but it takes time. It almost takes planning. You have to, even if you don't have to buy it, you have to click download. You have to wait for it to download. Increasingly, you were allowed to watch it as it was downloading. But if you'd already seen half of it, you perhaps have to wait until it was half downloaded in order to watch and skip forward to that point. So even on a fast connection and on today's connections, that would take a long time. That's not the experience we want. It's not the experience we've had with TV, even though you can choose what you watched in the sense that you chose the channel would turn on almost instantly. Yeah, okay, you couldn't choose what program was on the channel at the time, but you got that instant satisfaction. So where's that coming from? That's what we need from streaming. Thinking back to broadcast a little bit, streams are, of course, they start where the transmitter is or the encoder. They then come towards the receiver, whether it's a TV or something else. I mean, analog signals are streams. You would normally say they're information on their data, but they are coming at you. You are going to receive them whether you like it or not. MPEG-2 transport streams is a technology which is widely used in digital TV and for many other online applications. It's a way of wrapping up multiple videos and audios into one stream, which you can then send to a certain place. So that's ideal for broadcast because it made what was a continuous information stream, which essentially was analog. It made that into a digital form. So they are, MPEG-2 transport streams are used in RF and still today for Freeview, FreeSat, and other applications like that. The online streaming initial attempts were things like RTMP. RTMP is based on Flash, Adobe's old format, and that is a way of streaming and sending MPEG-2 transport streams. So it's useful on networks. There's a way of pushing that forward to a destination. A more modern format is WebRTC. And WebRTC started for video conferencing, and for that reason, delivers sub-second streaming, and it's really important, of course, when you're talking that there isn't really any delay. So those are all examples of these streams where the source has all the data and it pushes it to the receiver. So if we think about transmitting over the air, it doesn't really matter how much, fine. If somebody transmits on top of the same frequency, that can be an issue. But I can start something on one frequency. Someone else can start something on another frequency. My house could be bombarded with hundreds of radio stations, hundreds of TV stations. But it doesn't make any difference to me. I'm going to pick up my TV. I'm going to tune into what I want, and I'm going to enjoy what's on there. It doesn't work like that if you want to do the same in a network. Networks have got a certain capacity, whether it's 10 megabits, 100, 1 gig. It's not that hard to run out of capacity, and indeed your computer might run out of computing capacity to deal with all of this data. So what we don't want to do on networks is broadcast everywhere, everything everywhere. So we use something called multicast. Multicast is a way of allowing parts of the network to opt in. So a computer might say, yeah, I'm very interested in having this particular stream, but I don't want all the others. And so by default, it wouldn't receive any of the others. But I could have my encoder, whether it's in my own building or if it's like a cable system that could be hundreds of miles away, but I've got the encoder and it's saying that anybody who wants me can pick me up. So this sounds to me like it solves a lot of the problems. We're not flooding the network with data. The network itself delivers the stream efficiently. Multicast, on the other hand, isn't adopted by the internet. There are a few reasons for that. But fundamentally, whatever the reasons are, it means that we can't use this kind of fairly elegant way of delivering video. We can't use that on a global scale. Multicast is because it is about streaming right now. Video on demand is more about getting what was streamed earlier. So it doesn't really help too much for video on demand. You may as well just download it as files, as we'll discuss later. And also, are the companies that provide services going to make more money, or are they going to make less money by delivering less data? Well, there is a commercial incentive to deliver more data. So that and some other reasons mean that multicast hasn't really taken off, despite some attempts on the internet. So we need to think about really what we're going to do then. Streaming kind of is intrinsically, it's like a gradient. It comes from the source and it goes to you. Into the internet, the way it's created and has been rolled out, partly for security. My router at home isn't going to just allow anyone just to send in video to me or any data at all, because who knows what that data is going to be. It might cause a problem, and I want to protect myself. I don't want viruses. I don't want people to be able to hack in. So there are these defenses against people sending you data. And of course, what do I want to do? I want people to send me data. So I have to ask for that data. I can't just send a video stream anymore people at home on the internet. So what we're going to look at is technology which pulls in that data, and HLS, as we'll see in a moment, is one of those technologies. One other downside to this traditional sense of pushing out data to whoever wants it is that typically you're constantly encoding things, and encoding costs money, whether it's costing you money in the cloud for computational cycles, how long have I got to turn this computer on, or if it's costing you money in terms of the amount of power it's using. Either way, if I can reduce the amount I encode, that's better. So if I'm constantly encoding some video and sending it out to people, even though it's the same video that I sent out 6 hours ago because I'm repeating a program, then we are faced with an inefficiency, and it's not necessary. Also, the internet has been built on caching, which means storing some data to deliver it again and again and again. There are certain things that people need, and you can store that locally and save on data. That isn't possible if you're always delivering new encodes, new data. So really, we can look at this as an evolution on top of what we've done before. We started with the analog, no delay, high RF bandwidth. So what we did is we introduced a bit of delay as a consequence of having digital, which allowed us to have perfect reproduction and more channels. And now on the internet, well, we can still have perfect reproduction. And we can, on top of that, watch what we want anywhere. Everywhere is possible, and of course anytime. So whatever we want. The way to achieve that is with chunks. So we've tackled this a little bit already. Why can't we just download the file? It's going to be too big. You're going to wait a long time, and moving around that file could be problematic. So, if I wanted to skip halfway through, well, why don't I just split the whole thing in half and I'll download the second half? Well, that's great until I actually want to be 3/4 of the way through. So I have to split it into 3/4, into quarters, and then I'll just download the last quarter. Why not, carry on and do tenths or hundredths or thousandths or 10,000ths of the file? Let's cut it up into really small pieces, because then we have an absolute choice of where we want to start. That reduces the startup time, brings it really down, and allows us to move around it. So this is really where HLS should enter our thinking. HLS is still one of the most popular formats that we have for streaming today, and it was introduced by Apple in 2009. And it's short for HTTP live streaming. So we know what streaming is. It's live because it's delivering it as and when we need it. Okay, it's not a live program, but on the other hand, if I say I want to have all of the video from 10 seconds in or 10 minutes in, then as I ask for that, then live, it will deliver what I need. And it does that over HTTP. And this is one of the reasons why it was very popular. Of course, being tied to Apple, that really helps. It had a lot of momentum back then, and all the more so now. So that helped the adoption, but also the reason it was successful in the long term is because it was built on these technologies, which are well known. So HTTP is the same technology we use to deliver websites, or HTTPS. That's what it uses, and it's everybody knew how to use that really well, and so it was an easy technology to deploy. On top of that, it seamlessly allowed you to move from one quality to another. So if we just look at HTTP for a moment, all websites are simply just a collection of files. You might go to a website, the first thing you get is the HTML file. That's the main heart of it. It tells you what's going to be on that page. And then from that, you'll get all sorts of other, often hundreds of different files. There'll be essentially programming code. It'll be downloading its JavaScript. It'll be downloading lots of different pictures. What are these? Well, even if it downloads a font, it's just a file on a computer. So a website is it's a collection of hundreds of files. And so we know how to deliver files at scale. We'd already learned by 2009 how to deliver websites which could take hundreds of thousands of people per second trying to read read the same page to find out what that article said. So why not split up the video into short sections, meaning into short files? So let's say we just cut down the time and split that video into 10 seconds. However many sections that is, we'll take 10 seconds at a time, and we'll encode those into a file, and we'll just call those files chunks. So it's these small, short files. All we need to do really to simulate having a stream is just to download chunk after chunk. As long as they're next to each other, we can just play them seamlessly together, and it will be as if we've pulled those in. We've requested each one of those, so it's come to our firewall, but it will be just as if it was being streamed to us. So each 10 seconds of the video is taken, it's encoded several times into different bit rates and qualities. And these files that we've created, these chunks, they are all representative of that same 10 seconds, but they'll be different sizes, because we might make one HD, we might make one SD, so there's less information to encode. It's going to be smaller. Why are we doing any of that? Well, fundamentally, it's because we come back to what we mentioned earlier about the internet being a little bit unreliable. The internet here really extends all the way to your device. So the internet doesn't really encompass your Wi-Fi, but when you're receiving a video, it certainly does. So your Wi-Fi might be varying. Your network conditions locally are going to be varying. So if you share a household, you might suddenly find that two other people start streaming. So your 40 megabit link is now being shared and cut into your bit rate. Effectively would be a third. So all of a sudden you're watching a nice 20 megabit UHD feed from Netflix. There isn't the capacity anymore on your network to do that. So what we then allow by doing this chunking is we allow for a player to choose whether it wants the big chunks or the small chunks, depending on what it sees is happening at the time. So this example here, we've got 5 segments of 10 seconds each. We start off and it's going really well. We're watching the chunky, the high definition video. During the download of that 10-second chunk, the second one, we realize that it's taking quite a long time to download, and so we think, well, perhaps it's not going to, next time we download something, it's going to take longer than 10 seconds. So let's choose the smaller chunk. That'll be the conservative thing to do. We'll download the small chunk, see how it goes. Download that chunk. That took quite a long time to download. Right? Everything's happening in time, but if we need a 10-second chunk and it takes 9 seconds to download it, we have to think, do we want perhaps to download a smaller chunk, because we want that the certainty that it's going to arrive in time. And that's exactly what happened. By the 4th 10-second segment, we've gone down to that smallest possible file in this particular example. And then we've realized that the network has improved a bit, so we can go back up. So it may well be in this situation that the viewer has spotted a difference between the HD that was 20 seconds in down to the SD or the even lower quality at the bottom. But what's more important is they haven't seen any black. They've not had to wait. I'd rather hear a video personally than have nothing. And so, if you're going on the train, going through a black spot, you need something which is going to keep up with you. It's going to keep delivering you some form of entertainment, but you're willing to accept a compromise. So this is just a very quick nod to how we deal with all of this. If you imagine a film on Netflix that's going to be, who knows, 90 minutes long or longer, how many 10-second chunks are there going to be? And times how many different qualities. I've used an example of 3, but there are going to be more for major services. So those are kept track of, well, very simply, by text files. So it's a little bit bizarre, I think. It's a very basic and usually human readable way of keeping track of these things, but it's absolutely true. If you ever get a link which has got M3U8 on the end, then you can just download that, load it into your text editor, and you'll see that it has information about URLs, so you can actually reconstruct how to get these different files, put it in your browser, and you can get that new file. You can see the bit rates that these are based on. So that's there, and they're all linked together. So you've got this master document that says, if you want high bitrate, go and read this file. If you want medium, go and read that file. And then when you read those files, then you actually get those links to the chunks themselves. And that's exactly what your player will do. We're going to talk in a minute about MPEG- as opposed to HLS, which we've just covered. So if you see a .mpd file, that's the text file for those. And these text files, they grew out of what used to be called playlists back for when they were created for just sequencing audio, but they're called manifests when they're used in streaming. So overall, we've found that HLS, very popular format protocol for delivering video online. It chunks the stream, and it uses existing technologies which were well understood. Got HTTP, which is what we use to deliver websites. And CDNs, for example, these are the infrastructure which delivers the files as close as it can be to your location, because it's that distance. Light only travels at a certain speed, and signals down cables only travel at a slower speed. So the closer that data is to you, the lower that latency is. But we've been talking about things like Netflix, big business. As a recording, Disney Plus is just launched with millions of subscribers. So clearly, these people are going to have some kind of thinking of economics, and it's all very well getting the subscriptions. You may well have a profitable business, but how do you make that more profitable? What are your risks, and what are the ways to reduce your costs? Well, that's really can be answered partly by increasing standardization. That's what we'll look at next. So standards in terms of technology have a very specific meaning, and that is it's been through a standards body. It's a internationally recognized organization which deals with requirements and meeting those requirements in a very structured way that allows for people to agree that that's the right way to do it. It tries to counterbalance against commercial interests, and capture other aspects to make the technology as useful as possible without helping any one individual or organization. So it's actually in the interest of the providers themselves to have standardization. It's not so much in the interest of the technology vendors, who of course have come up with this idea to start with, and they want to capitalize on it, they want to make money out of it. The two can coexist, but the reason standardization is important is because when you are a streaming provider, anybody who wants to deliver video just really needs to know that video is going to work. They don't want to have to do lots of testing beforehand. If I have a new provider come to me, I'll give you a video, yeah, let's do a year's contract. I don't want to have to spend a month testing that it's actually going to work and checking for edge cases. I want to feel that I've got a really good basis. They knew how they're supposed to deliver it. I know how I'm supposed to receive it. That's what standardization does. It also stops what the alternative is a company that is owning or driving a certain standard, they may choose to make that suddenly incompatible, maybe for really good reasons. We found a better way of doing it. All of our customers want to do it this way, and it gives them really big benefits. It does mean, though, that we're going to have to stop working in the old way, and that may be something that's incompatible. And then you're left as a streaming provider having to deal with the people who can only use the old technique, and you have to create a new version for the people who do new techniques. So this is where we start realizing that there is money to be saved. If I'm able to reduce the amount of encoding, the number of chunks that I'm creating, then I can start saving money in, again, encoding costs money, either for paying for electricity or paying for time. And then storing it, saving it, how many versions do I want to save? Well, I want to save one version. I don't want to have to save 2, 3, 4. Another interesting aspect is licensing costs. We're talking patents here. Standardization doesn't solve this problem. It can shed more light on it, but as we've seen recently with MPEG-, the idea of having a patent pool and bringing that together so that everybody has a one-stop shop to pay their money, so they know they can safely use the technologies involved. Doesn't always work, but when it does work in terms of MPEG-LA for APC, we've seen a wide adoption there. So quickly, just to look at some of the standardization bodies, just to put them into a bit of context, we've got people like the IETF, who are very well known for standardizing internet-based technologies. TCP/IP, that we very fundamental technologies that we use day in, day out are standardized under these guys. And with it, W3C, they are helping standardize WebRTC that we spoke about earlier. MPEG, unsurprisingly, is involved in MPEG- and CMAP, but also behind the scenes ISO is as well. HLS is almost a standard. They've issued many drafts into the the IETF. I think we are perhaps on version 7 or so now. So at least it's documented, even though it hasn't gone through the standardization process. Things like RTMP, well, we're now going into Defacto Standards. RTMP has a specification document. It was created quite a long time ago by Adobe. It's based on Flash. That whole thing has been end of life now. It's an obsolete format almost. But so they put a specification document in towards the end of its life to help people. But that was always a de facto standard when it started, because so many people were using it, but nobody really knew that much about it. It was controlled by a company. So obviously de facto standards, they're not really standards at all. So Dash, I really just want to introduce this in terms of having that familiarity. We've got HLS that we've talked about. We know that's a streaming format. Dash as well is a streaming format. And it works similarly to the way HLS does. So there's no need to go into the details. It uses chunked encoding. We mentioned it already. It has manifest files which are similar. They're called .mpds instead of MP308s. And they have got slightly different information in. The technology itself is based upon an ISO standard container format, and that's based on QuickTime, also known as fragmented MP4. That can contain a number of different codecs, so it's got flexibility. And the idea of Dash was to have one format which has that openness to it and the ability to keep adding and be extensible in the future. And that's what Dash has delivered. It supports ABR, which is adaptive bitrate, which is this idea of creating chunks at different bit rates. and it has this end-to-end open media chain. So even things like encryption, the common encryption algorithm here, so mechanism, that allows you to put DRM on. Of course, that's really important. A lot of people don't like it, of course, but at the end of the day, that is how the business is built. That's how people protect their assets. So you need to have DRM. And this allows you to be able to have multiple types of DRM in the same chain, and for players to talk to the provider that they work with. So we've looked at the standardization. We've looked at things like MPEG-, which have brought a little bit of sanity and stability to these protocols. Just a nod to the future is called for here, really. It's interesting times. ATSC 3.0 is a standard that is big in America, but it's also being picked up by other countries, such as South Korea, and also down in South America. So, that is delivering, possibly for the first time, IP over a normal terrestrial transmitter. So it's instead of technologies like DVB Freeview here, which uses kind of co-FDM modulation, which is sending certain bits to you. This is exactly the same as plugging in an Ethernet cable. It might be one direction, in the sense that you can't send back to that same transmitter, but all of those packets coming in are exactly the same as IP would be. HBBTV is a version of hybrid television where, yes, you've got that normal transmission, RF transmission to you, but it allows the box to seamlessly mix internet delivered services. DVB-I is a new format from DVB, which is for delivery over the internet. So that is creating IP based broadcast technologies is a way that broadcasters, particularly public broadcasters, are going to do their best to remain relevant, and on top of launching their own internet specific services. And ultra low latency streaming is very much in vogue. We've done a lot of great work in making streaming pervasive throughout the world, really. And now people are saying, well, actually, I do like watching quite a lot of sport, and it would be great if that wasn't 30 seconds, 40, 50 seconds late. Because remember, we were originally talking back in 2009 about 10-second segments, and if you had to buffer 2-3 of those, then that's 30 seconds of video in the bag that you haven't watched yet. So how do we do this so that we can safely deliver video very, very quickly, but also keep in that safety margin that we talked about, needing safety margin in case your network suddenly goes bad, and you need to play some video that you've already received whilst you download a new chunk, which is taking longer than you expected. So CMAF and low latency HLS are two formats which have been developed in order to achieve that, and that's on top of things like WebRTC and WebSockets, which deliver streams over the internet. So these are very much in development. Low latency HLS has only just been released a few months ago by Apple, and certainly hasn't filtered through into implementation yet. So these are yet to come, and I'm sure much more. So we've had a look now at why we want to do streaming, how we've moved down the road from the very first transmissions of radio and television onto streaming on the internet, and why that's better in some ways, and the future may well be that it's low enough latency that it starts matching what we've been used to, the broadcast signals that we've been used to. So that's the online primer. Please do keep in contact. If you have any questions, feel free to email me at the webinar at thebroadcastknowledge.com. Emails on this screen. Any questions in general, you're more than welcome to join our group for IET Media on LinkedIn. And we look forward to seeing you there. Thank you very much. Look forward to seeing you on the next video from IET Media.